So the Schrodinger equation, of course, was of this form: d2 psi dx2 plus twice m by h cross square e minus half m omega square x square times psi equal to 0. And then we made this change of variables that x is alpha z and chose alpha to make this coefficient in particular simple. The question that was asked is, do I have to do this? The answer is no, you don't have to. But if you don't do it, your algebra is going to look a lot messier. And of course, a messy algebra is one in which there's a bigger chance of making a mistake. Apart from that, there is another very important reason why you should do this, which is if you want to solve this equation on a computer, and although we do know how to solve this one exactly, most quantum mechanics calculations cannot be done exactly. You have to do some kind of approximation, and sometimes you solve it on a computer. Well, very often you solve it on a computer. And when you are dealing with a computer, dimensionless quantities are always a pain, especially dimensionless quantities whose magnitude in ordinary units is very, very unusual, something like either huge or very small. For example, h cross, of course, in ordinary SI units would be abnormally low. Okay. So the problem with dealing with such things on a computer usually is this: computers work to only finite precision. So if you actually have a number which is very, very tiny in your calculation, there's every chance that the computer will encounter round of errors when you're trying to calculate with them and give you bad results. While this used to be a very severe problem early on when you had, say, single precision computers, now you have double precision computers, you have you have actually 64-bit computers where you can use double precision. So these problems have become less. Even then, it's always a good idea to deal with dimensionless quantities which are adapted to the problem that you are trying to solve, so that in those units, effectively, remember when you are doing this substitution x equal to alpha z, you're really using alpha as a unit of length, and then z becomes dimensionless, and in these units z has a magnitude of the order of 1. Whereas in a atomic system, for example, x would have an would have a size of order 10 to the minus 10 meters. Now, dealing with 10 to the minus 10 meters is not really that much of a problem with multiple precision computer programs nowadays. However, it's always a good idea to try to get everything to similar dimensions rather than have one large number and a very small number. Whenever you try to add a large number to a very small number, you end up sacrificing a lot in precision, especially in finite precision computer algorithms. So with that point of view in mind, it's always a good idea to try to substitute variables as much as possible. And so that was one question that was asked. The other question which was asked was basically one about regular singularities and regular singular points. Now, I'm pretty sure most of you have already taken a look at that issue, but let me still clarify this because this is very, very important. There are two different kinds of objects here. One is the function that we are talking about. The other is the ordinary differential equation that we are talking about. And basically, the terminology for singularities is really a terminology for the function. And there you have a regular point for a function, a point where a function is analytic, that is a point about which the function can be expanded in a power series, or singular points of a function. All this is about functions. We have not come to ODEs yet. And among the singularities, depending on how severe the singularity is, there are actually 4 kinds. One which we hardly ever bother to talk about, so-called removable singularities, which are such that they can go away simply by redefining your function at a point. I hope everybody knows what a removable singularity is. The other one, again, I'm pretty sure everybody knows what these are, but still it's important to recapitulate them. You can have poles, you can have branch points, and you can have essential singularities. And as I've been saying over and over again, this last kind is the worst. Essential singularities really are very, very bad things as far as analytic calculations are concerned. And you would want to avoid them as far as possible. Or if you can't avoid them, then you have to sort of take special care when in a region where a function is expected to be essentially singular. By the way, you have to take special care for poles, branch points as well. It's just that essential singularities are much more difficult to handle. Okay. So, are there any is there any confusion about this so far? Anybody who has a confusion, please speak up. Okay, since there's no response, I'm assuming I'm still audible and still connected. So, since there's no response, I'm pretty sure everybody knows this stuff. But the connection between that and singularities of an ODE is sometimes confusing, especially because very often the nomenclature is similar. So we were talking about second order linear ordinary differential equations, SOLODE for short. I will just say ODE, and since most of the differential equations we are going to deal with are second order anyway, we are going to just say ODE instead of saying second order linear and so on. Okay. Now for ODEs, the nomenclature goes along similar lines, which is really the major reason for the confusion. So regular and singular, that's the first division that you make. So same kind of division as for functions. And here the nomenclature is pretty straightforward. If you're talking about second order linear ODE, there are two independent solutions, and regular simply means both independent solutions are regular at that point. So again, once again, this is a statement about a point that the ODE is regular there. If the ODE is regular there, both its independent solutions are regular functions. So that nomenclature is pretty straightforward. Now when it comes to singular, what it means is, of course, is the contradiction to this, and that means both independent solutions cannot be regular. One can be regular, and the other will definitely have a singularity. Okay, so singular, of course, both can have singularities, but both cannot be regular. That's the only thing that we are talking about specifically when you're talking about singular points in a ODE. And among these singular points, you have a division of two kinds, which are regular singular points and irregular singular points. So this is a nomenclature which is used actually only for ODEs, not for functions. Functions, you have singular points of function, and that is of four different kinds. When you're talking about ODEs, singular points are where at least one of the two independent solutions is bound to be irregular or singular. Not necessarily both of them, but both can be. And now you divide singularities into two different kinds, basically depending on this kind of behavior of the solution. That is, if the solution is essentially singular, then it's bad, and that's what you really want to be warned about. So an regular singularity is one in which both independent solutions are not essentially singular. By the way, since you have a singularity, okay, one of the solutions has to be singular. There's no escape from that. One can be regular, the other can be singular, or both can be singular. But what we are insisting on is both be free of essential singularities. If that is the case, you say the point is regular singular. And irregular singular means at least one solution, or both, but at least one is essentially singular. Okay, so this is how the classification really goes. Unfortunately, some textbooks mess up these words, and That is a source of potential confusion. So this is important to stress. And the other is because these words are so similar, it's very often possible to confuse them. You don't talk of essential singularities of an ODE. You talk of essential singularities of solutions of an ODE. You don't say a solution is irregularly singular. That doesn't make sense. A solution can only be essentially singular or can be a branch point, can be a pole, can be removable singularity, typically not in the case of an ODE, or can be regular. Okay, that's the classification for functions. So this is very important. You have to be clear about the classification for functions as opposed to classification for ODEs. Trouble is, they sound very similar and it's pretty easy to confuse them. And the reason why they sound similar is that they are related to each other. The nomenclature for ODEs is based on the kind of behavior that the solution can have. So let me now stop about this, but let me ask you, does anybody else have any question about this? None. Okay, great. So let me now do one thing which I forgot to do in the last class, which is I responded to a question which asked why is a regular singular point of a differential equation, second order linear differential equation, the way it is, that is, why is this criterion at all true? Pz dy dz plus qzy equals 0. Of course, as most of you know, in fact everybody knows, that a regular singular point z equal to z0 is characterized by the fact that Pz at most a simple pole. So Pz is at most, if it's singular, it is at most a simple pole at z equal to z0. And Q of z at most a double pole. Okay, somebody, I don't forget whom, asked, why is this the case? That is, why is it that this criterion actually tells you? Remember, this is what is often passed off as a definition of a regular singular point. And as I tried to explain in the other day, this cannot really be a definition because it is way too sort of peculiar to be a definition, right? The real definition is both solutions are essential singularity free. And as a consequence, you can use Frobenius method to solve them. So the question was, why is this criterion at all correct? And the answer to that requires a bit of advanced, well, not advanced mathematics, but quite a lot of complicated math to answer in full. I'm not going to bother doing that. If you're interested, you can, of course, read up any decent differential equations book. When I say decent, I mean not one in which just some problems are solved, but one in which things are explained, like say Birkhoff, Rota, or Inche, or whatever, the books that I mentioned in the last class. Okay, but what I will tell you now are 2 points. One is, if P of z had more than a simple pole, the Wronskian, which involves exponential of the integral of P of z, that will be rather badly behaved, right? Because if P of z had a simple pole, if P of z was regular, then integral of P of z basically would be a regular function. No problems there. You have an exponential of a regular function in your solution, which is not a problem. On the other hand, if P of z had been a simple pole, you end up with integral of 1 by z minus z0, which gives you a log z minus z0. When you expand that, you end up with a power of z minus z0. When you exponentiate that, because that's what the integrating factor is. So even in that case, it's really a rather simple thing to handle. On the other hand, if you had more than a simple pole, then the Wronskian would have a factor which has exponential of at least 1 by z minus z0 or more. And that is a sheer shot prescription for getting a essential singularity. Right? Exponential of a negative power of z minus z0 is certainly going to give you arbitrarily large number of negative powers of z minus z0, and hence will give rise to an essential singularity at z equal to z0. So why p of z can be at most a simple pole can be understood simply in terms of the Wronskian of the differential equation. Any confusions about this? Okay. If not, let's just talk about why q of z can be at most a double pole. This is something which, which is essentially something you already know. It's in terms of, yeah, go ahead.
Sir, what is the Wronskian of the differential equation? Is it the factor we multiply to make its Sturm-Liouville form?
Almost, except that basically it's you don't even have to go to the Sturm-Liouville form for this. If you have an equation like this, so if you have two solutions to this, this solution 1 obeys this, and you can multiply it by y2, and then you put in the equation for y2, which is like this, multiply that by y1 and subtract, then of course this term cancels out, and you get y1 y2 prime minus y2 y1 prime equals something, and that y1 y2 prime minus y2 y1 prime is defined as the Wronskian. It is related to the Sturm-Liouville equation. It is used in the Sturm-Liouville form, but you don't have to go through Sturm-Liouville theory to come to that. This is what the Wronskian is defined to be. And the important thing is, if you know the Wronskian, then because the Wronskian is really d of y2 by y1 divided by y1 square, right? Well, y2 by y1's derivative divided by y1 square. That's something you can easily see. So if you know the Wronskian, then y2 will simply be y1 times integral y1 squared w dz, right? This is an indefinite integral that you have. So if you know one solution, the other solution can be computed from it once you know the Wronskian. And what equation does the Wronskian obey? It's easy to see that the equation that the Wronskian obeys from the differential equation is this. The derivative of this Wronskian is nothing but y2 y1 double prime minus, sorry, I wrote the same thing twice, y1 y2 minus y1 y2 double prime, and what you have is really this, right? That is, you write down the differential equation twice, once for y2, again for y1, multiply the first one by y1, the second one by y2, and then subtract. You end up with an equation for the Wronskian. This is exactly what we did for, say, for the oscillation theorem, say, or the proof of no degeneracy. We essentially use that because the Schrodinger equation also, of course, is a second order linear differential equation. But this immediately tells you that w prime plus pw equals 0. So w is, apart from a constant, is e to the minus integral p dz. So there are 2 points here. First of all, w is given by exponential of the integral of minus p dz, which is what is going to sit here to give you y2 from y1. So even if y1 were a regular function, if w had an essential singularity, then y2 will end up with an essential singularity. Okay? So if w, which is the exponential of minus integral p dz, if p has more than a simple pole, even after integration, it will still have a pole. So you'll have e to the power minus 1 by z minus z0 at least, if not higher powers. And that is an essentially singular function. And since the Wronskian is essentially singular, even if one solution is regular, the other solution is going to be essentially singular. So that's the reason why P cannot be more than a simple pole. Okay? Any questions about this? The answer to the question about Sublabel is yes, it is used in Sublabel, but you don't have to know Sublabel theory to understand this. It's basically simple differential equation theory.
Okay, sir.
Okay, and the other part is, well, let me just move to a new page. So this is the equation that we are trying to solve by power series method. But by the way, you cannot use power series method if z equal to z0. Okay, let's say z equal to 0, just for simplicity. I'm just putting z0 equal to 0 for the time being, just so that I don't have to write z minus z0 everywhere. So if z0 equal to 0 is a regular singular point, what you can do is try a Frobenius solution. And Frobenius method will give me one solution, at least. It can give me both, but it's guaranteed to give me at least one of the two solutions, as you must have seen before. If you don't get both solutions using the Frobenius method, then then the solution actually has a logarithmic kind of divergence, which you can also, or a branch point singularity kind of logarithmic kind of thing, which you can also figure out once you know one solution. I'm pretty sure all of you know how to do that, right? I don't need to explain Frobenius method and the singular cases of the Frobenius method, right? By the way, this word singular is an English adjective, has nothing to do with functions. I mean the special situations which arise when you don't get two independent solutions using the Frobenius method. You know all that, right? Of course, whenever such a question is asked, it means if you don't, please speak up. Okay, and the next part here is, yeah, it was not done in that much detail. Okay. Okay, I don't really want this to become a mathematical physics class, although this does seem like a mathematical physics class for me sometimes. But let me see. Okay, I will talk about that later, not today. Later, we will have occasion in quantum mechanics to find equations where there will be a problem. So we will try to talk about that in that context. But anyway, the basic idea is, okay, let me state this as a statement right now. The Frobenius method will either give you both solutions, both independent solutions. Sometimes it fails. Okay, when does it fail? When the indicial equation you get out of the Frobenius method happens to have equal roots, then this does not give you two solutions, it gives you only one. And the other one is when it gives you, well, two solutions, two roots which differ by an integer, then there is a chance that one of the solutions that you get is either identical is 0 for out of consistency or is a repeat of the other solution. So once again, in such a situation, you fail to get two independent solutions. You get only one. And then, of course, you can get the other one just by using the Wronskian, or you could use some special tricks. But those special tricks essentially ultimately end up giving you at worst a log z times the original function plus some other power series. So the log z essentially gives you a branch point kind of singularity, which is not due to a power. There are two possibilities. You can either have z to the power s, where s is this index, where s is a fraction, in which case this is a branch point, z equal to 0 is a branch point, or you could have a log z. This is the other kind of branch point which you get. Now, of the two, Frobenius essentially handles this one. The way you start with the Frobenius method, of course, is that you assume that the solution y is of this kind is Cn z to the n plus s, where n goes from 0 to infinity. So the singular solution that you get here is singular basically because either s is negative, in which case you have a pole, or s is fractional, in which case you have a branch point. The other kind of branch point that you can have when you have a regular singular equation, singular point in the equation. You're trying to find a solution about the regular singular point is the log z, which Frobenius will not give you directly simply because your assumption is that it's a generalized power series, right? Log z cannot be written down as a bunch of powers of z. So the basic problem is that the Frobenius method will not give you this solution. So if your equation has a solution of this kind, the Frobenius method is bound to fail, at least is bound to fail to give you two independent solutions. In those cases, you get one independent solution from Frobenius, the other by some other method, by using the Wronskian or by those specialized tricks that people sometimes use. Not really very important tricks. Ultimately, they are just ways of solving an equation. They will be useful, so we will talk about them when we find occasion to use them. Okay, but before we fold this up, let me just tell you why is it that this P of z equal to 1 by P of z not worse than 1 by z and Q of z not worse than 1 by z square. Where does that come from? So let's just assume that P of z has a pole of order, let's say m. So I'm going beyond the regular singular point here, or at least I'm assuming that P of z, that we can do a Frobenius kind of solution even if the pole is some other order. So P of z will be something like 1 by z to the m into some analytic function, right? That's what a pole means. Is everybody okay with that? If you have an order m order pole, it means that if you multiply P of z by z to the m, the resulting function becomes an analytic function. What am I writing? Plus pi to z square plus higher order terms. Right? This is the general form of a function with an mth order pole. Unless a Q of z has an nth order pole. So n and theta 0 plus theta 1 z plus theta 2 z square and so on. So this is what I'm assuming. Okay? That P of z can have a higher order pole, Q of z can have a higher order pole, any order pole. And let's see how this tells me that m cannot be more than 1 or n cannot be more than 2. If you want a solution of this kind, Cn z to the n plus s, sum over n equals 0 to infinity. Now for this, let me remind you that what you have to do in the Frobenius method is plug this thing into the differential equation, write down everything, match all the coefficients, all the powers and so on, and then find out what is called an indicial equation. So what exactly is the indicial equation? Can anybody tell me that? And where does this come from?
That the coefficient of lowest power of z after the substitution gives you the indicial equation.
Okay. Can you explain why? You're right. But why does that give you an equation for the index?
Because when we differentiate the index comes out. I mean, it is multiplied with some number that depends on the index.
True, but the other terms. Okay, I guess you have missed my point. You're right, but my point was you get recursion relations and you get the indicial equation. The recursion relation essentially gives you connections between different coefficients, differentiants, and the indicial equation gives you a value for s. Why is it that the indicial equation, which as you rightly point out, comes from the lowest power of z after you substitute, why does this give you the s and not a connection between the coefficients? Okay, first, is there a restriction on these coefficients? Any restriction?
This should be the input given to the differential equation, right?
What? Sorry, I couldn't.
One of the coefficients can be chosen arbitrarily.
Of course, but that's true. But is there a restriction?
Yes,
I couldn't hear the other answer.
0.
Which one cannot be 0?
The lowest order one. I guess.
Okay, that exactly is what I meant. C0 cannot be 0. This is one thing you know. Simply because if C0 is 0, then you will not call that C0. All you're saying is that this series starts with the lowest power of z to the s. Wherever it starts, you call that power s. And hence, the coefficient of that power has to be non-zero. Okay, that's the basic thing. Okay, and the important point is when you plug this into the equation, that is when you plug this in y double prime plus py prime plus qy equals 0, what happens is the overall lowest power, where will it come from? This one has a term c0 z to the s plus c1 z to the s plus 1 plus c2 z to the s plus 2 and so on, right? That's what y has. Y has this plus higher order terms. The lowest power that you will ever have must come from this. That should be sort of obvious, because if, say, this term gave you a power, this one would have given you one lower, always. Is it okay? That is, whatever terms you get, the lowest power will always originate from the C0 to Z to the S, and then of course you will have to differentiate and so on. So can anybody tell me what will be the lowest power of Z from here? The power. That's simple, right? You just take this and differentiate this twice. What's the lowest power that you're going to get?
S minus 2.
Of course, obviously, S minus 2. And what will that term be? Okay, let me also write down the term. The term will be C0, okay, S into S minus 1 into Z to the S minus 2. I'm just not writing the Z to the S minus 2 here. Okay, what will be the lowest term from this? Can anybody tell me that? What lowest power? From this term?
S minus 1.
No, S minus 1 is from Y prime. From this whole thing.
S minus 1 minus m.
I'm pretty sure everybody is sure about this, right? S minus 1 from the derivative and minus m because P has a 1 by Z to the m. Right? Is that clear to everybody? Okay, so that means
Yes, sir.
the coefficient there will be C0S times pi 0. Again, pretty straightforward. S from the differentiation, C0 was already there, and you have this pi 0 which is coming from P. So quickly, what about this? Lowest power?
S minus 1 minus m.
S minus?
Sorry, S minus 2 minus m.
S minus 2. Why 2?
Oh,
S
sorry,
minus m.
sorry, S minus
It's just S minus n. No derivatives, right? So now the question is, among these, the lowest ones will give you the indicial equation because that will involve only C0 and no other coefficient. And C0 cannot be 0, so whatever you get, after all, every coefficient has to vanish. And since C0 cannot be 0, whatever you get will give you an equation for S. Is that okay? This one, of course, will have C0 times theta 0. That's the coefficient of S minus n. Now, the question is, when you add the lowest powers together, the coefficients of the lowest power together and equate that to 0, that gives you the indicial equation. What kind of an indicial equation will you get? Will it be linear, quadratic, or what?
Quadratic.
Does everybody agree that we are going to get a quadratic in each indicial equation? No, not really. That is exact. You always have managed to get a quadratic indicial equation simply because you have been dealing with regular singular points. Now you should see, this should be very easy. The indicial equation comes from the lowest power, right? So question is, which one is the lowest power among the three? This one gives you a quadratic piece. This one gives you a linear piece in S. This one gives you a term which is independent of S. Okay? Clear? Right? So when will the quadratic piece at all be there in an indicial equation?
When m is less than equal to 1 and n is less than equal to 2.
Exactly. If when m is less than equal to 1 and n is less than equal to 2, then this cannot be lower than s minus 2. This cannot be lower than s minus 2, which means the lowest power will be s minus 2 because s minus 2 is already here. So this term will definitely be there in the initial equation, and it might also have this term and this term. That might be there. That is, if say m is 1, then the initial equation will be this plus this equals 0. If m is 1 and n is 2, then it will be this plus this equals 0. But if m is say more than 1 or n is more than 2, then the initial equation will not come from this term at all. It will come from either this one or this one, depending on which one is larger or more negative, or rather which one is smaller. That's more important. So can anybody give me a generalization? Say, look, what you want to do is take a look at the lowest power of z that you are getting in the whole equation after you substitute, and the coefficient for that will only involve C0 times some S's, right? Since the lowest power and all powers must have 0 coefficient, the lowest power must also have 0 coefficient. But that will give you C0 times something equals 0, and since C0 cannot be 0, that something has to be 0. So that's the indicial equation. The indicial equation is order 2 only if you have a regular singular point, because if you have a regular singular point, m is less than equal to 1. So this can be s minus 1 or s minus 2, right? It can't be lower than s minus 2, okay? Because m is bounded by 1. Here n is bounded by 2, which means this can at worst be s minus 2, cannot be lower than that. If say m is 1 and n is 2, then all of these will contribute z to the s minus 2, right? As the lowest power. So for m equals 1, n equals 2, which is the extremal case for regular singular points, the indicial equation will be s into s minus 1 plus pi naught into s plus theta naught equals 0. A quadratic equation. If say m is 1 and n is say less than 2, then what will happen? Then this will give you s minus 2, this will give you s minus 2, this will give you something higher, not s minus 2. So the indicial equation, which will be given by the coefficient of z to the s minus 2 again, will be s into s minus 1 plus pi 0 s coming from here equals 0. If m is less than 1, n is less than 2, then the initial equation will simply become s into s minus 1 equals 0. Okay? All you have to do is figure out where is the lowest power coming from. If m is small, then the lowest power actually comes from the second derivative and not from py prime or qy. On the other hand, if suppose, let's take one example. Let's say m is 3 and n is, let's say 2. Then what happens? This one still gives you s, the first one, the derivative still gives you s minus 2, The py prime term gives you s minus 4, that's the power of z, and this one gives you s minus 2. Among the three, which one is the smallest? Of course, s minus 4 is the smallest. And that since the other two cannot give you a term of the type z to the s minus 4, the only term which will give you z to the s minus 4 is this one. So the equation will become s pi 0 equal to 0. So that doesn't mean that, now notice that in this case, it does not mean that you will not get a Frobenius kind of solution. But since you get a linear equation, you can get only one s out of this. And so you're definitely going to get only one Frobenius kind of solution. In fact, in this case, the Frobenius kind of solution is going to be regular because s is 0 means z to the 0 plus something into z to the 1 plus something into z to the 2 and so on. Just a nice power series. But we have already argued that if P has a pole which is worse than first order, in this case, P has a third order pole, the Wronskian is going to be essentially singular, so the other solution is bound to be essentially singular. And you can see that from the Frobenius approach, that if you tried the Frobenius method, you will not be able to get a second solution because you end up with a linear equation. You end up with a linear indicial equation. By the way, if you had something like, say, m equals 4, n equals 6, well, can anybody tell me what the indicial equation be?
C naught theta naught equal to 0. So that's not true, I guess.
Of course, theta naught is not 0 because if theta naught had been 0, then the function would not have had a nth order pole, right? Theta naught had been 0, then this would have been, say, and theta 1 were non-zero, then theta 1 would have been the lowest term and the pole would have been n minus 1 order. If you're saying it's an nth order pole, that means theta naught is not 0. And C naught cannot be 0. What this means is in this case, you simply cannot get a Frobenius type solution at all. Okay? Clear? So the emphasis here is in the fact that if you want both solutions to be Frobenius type, you need to have a quadratic equation for the indicial equation for the index. And that you can get only if m is bounded by 1 and n is bounded by 2, because if that is not correct, then you will not get that at all. Is that okay? Any confusions about this? And what you must also realize out of this, that even when the m equal to 1, n equal to bound is not satisfied, there are possible Frobenius-like solutions. In fact, there will be a Frobenius-like solution possible as long as this gives you the lowest power. Right? Because then you will at least have an S in your indicial equation. What happens if S has a single value? That is exactly what you will get if you have a linear equation. Then you will get one solution of this kind, the other solution simply will not be of this kind, will not be a Frobenius kind. And the important thing is, we have already seen how to find the second solution, right? You can just use a Wronskian. But if, as we are saying, if m has a higher than first order pole, then the Wronskian has an essential singularity. So when you use that in an integral, it is going to end up giving you an essentially singular second solution. Always. Okay. Any further questions?
Sir,
Yeah.
Well, the initial equation is C naught theta naught equals 0.
Yeah.
Does that mean both the solutions are essentially singular? Because we cannot write a Maclaurin series for the solution.
That I am not very sure whether that's true. You can't write a Maclaurin series for the solution. Or this is really a Taylor series. I've just chosen z equal to 0. Z0 equals 0 for convenience. You can do the argument for any point. You cannot get a Taylor series, but I'm not sure whether this at all prevents a logarithmic singularity in one of the solutions. Remember, when you have a what kind of problems can you have with a function? What kind of singular points? A function can be nice and analytic. That's regular. Has a power series expansion, which of course is valid only within its radius of convergence, but at least this is a possibility. That's regular. You can have a pole something like this. That's an mth order pole. If m is a positive integer, of course, there's a pole only if m is a positive integer. If, on the other hand, you have a function which looks like this, and m is a fractional number or a complex number, not an integer, then this is a branch point. That is, z equal to 0 is a branch point. I'm just not bothering to write z minus z0 everywhere. So this is a pole where m is 1, 2, 3, and so on, some positive integer. If m is a fraction, fraction, I'm using the word loosely. I don't mean rational numbers. If it's not an integer or a complex number, then what you have here is a branch point singularity. Now, the last two, these both come under the Frobenius kind of solution, which really is not a Maclaurin series, by the way. The Maclaurin series is Maclaurin, whether you call it Maclaurin or whether you call it Taylor, is basically this. Okay, what this is, this kind of solution you are assuming here is something else. It's called the Laura series. And sorry about the Maclaurin, which I used a while ago. That was a joke. It's really Maclaurin. That fellow was English. Laura was French. His name is Laura. The Laura. Have you learned about Laura series before?
Yes, sir. I actually meant Laura series. I messed up.
Okay, I spelled this wrong. So this is a Laura series. Laura series is what has negative powers or fractional powers, possibly. Laura series actually has fractional powers. Negative powers. Fractional powers are the kind which have branch points. The other kind of branch points type solutions which can very well arise when you're trying to solve a second order differential equation have log z times some function. And this, of course, also is a branch point, because when you go all the way around the origin being the singular point here, log z changes. Why? Because z goes from r e to the power I theta, which is a log of log r plus I theta, to r e to the I theta plus 2 pi, or 4 pi or 6 pi, depending on how many times you're going down, or even minus 2 pi minus 4 pi, depending on whether you're going down the other way. But the log ends up getting an additional I2 pi piece or I4 pi piece every time you go down. So log z is a branch. Z equal to z0 is a branch point if you have a log z function. Log z is not covered by the Frobenius method directly. That's why you need those additional tricks. Either the Wronskian or the tricks that I keep on referring to, but which you may not have learned. Okay, since I've said so much, let me just quickly tell you how it's done. So, if you have a regular singular point, this will immediately give you a quadratic indicial equation, right? That's what we have been discussing so far. And so you will get two roots. But the problem arises in two cases. One is the initial equation may end up giving you repeated roots. S minus S0 whole square equals 0. Okay? Right? So what happens if you do that? What happens if such a thing happens? Then the Frobenius method, of course, will not give you two indices, and hence it will not give you two solutions. Right? But now, let me ask you this. Suppose I do not put S equal to S0, that is, I do not demand that the index satisfies the indicial equation, but I demand that the entire recursion relations are all satisfied. Do you understand what I'm saying? I'm saying that once you plug in the Frobenius kind of solution in the second order differential equation, you're going to get, ultimately you're going to get a recursion relation, right, between the coefficients. And you're also going to get an indicial equation. By solving the indicial equation, you can get only one solution, which is S minus S equal to S0. And that is the one which we have to use. Okay. Is that okay? Clear? So let's say what we do is we find out the recursion relation, find out the way the coefficients are related to each other without putting in the explicit value of S. So the recursion relation will involve S. Okay. And then take that function which depends on S. So this is this power series and plug it into the differential equation. Well, we have already done that. All I'm saying, already done that as a first step in the solution. But if you do this, if you put in f of s with every subsequent coefficient dependent on s, because you have not put in the value of s explicitly, that is, you have not put in s equal to s0, then can anybody tell me what y double prime plus pz y prime plus qzy will lead to? That will not be 0, right? Because to be 0, all coefficients must have given you 0. Here, what you have done is you have satisfied all the recursion relations, which means all the higher power coefficients are 0. But one term is still left, which is you are going to get this term basically. Is everybody clear about this? Okay, let me not write this. Let's say Ly, the linear operator acting on y. Whatever that linear operator is will ultimately give you this. Is everybody clear about this?
Excuse me, sir.
Yeah, go ahead.
I'm not sure if I was able to follow the argument. The one thing that I would understand is that you are saying, what if the case be that we are getting only one value of s?
Yeah, but what did we really
Only
get?
one
When
solution of s
suppose you
from
had
the
this linear operator y equal to 0, some equation, right? So what did you ultimately get? You got an indicial equation, which essentially would have usually been of this kind, right? A quadratic equation. I'm assuming regular singular point. So you get a quadratic equation for the index into C0 z to the power s minus 2. That's what you have at the lowest order term. And you equate this to 0, you get s is either equal to s1 or equal to s2, right? Plus you get a bunch of other terms. I'm just saying this is not necessarily true, but I'm just saying that it has Sn plus 2 into something which depends on n and s, a bunch of factors which depend on n and s. Let's call this alpha, plus Cn beta, again depending on n and s, into z to the power n plus s, and so on. Higher order terms. This is equal to 0. This is what I hope everybody realizes, that roughly this is what the solution to differential equations end up looking like once you're putting z to the n, cn z to the n plus s in the equation. Is everybody clear about this? Do you understand what I'm saying? I'm saying that you will get some powers, and the lowest order power is separate because it does not have two different coefficients stuck in. It has only one coefficient, namely C0. And because we are dealing with a regular singular point, this one power will be z to the s minus 2. And this will be n equal to 1 to infinity. All the next terms. Okay, could be, in fact, by the way, I've just written down a two-term, two-step recursion relation. Could be Cn, Cn plus 1, Cn plus 2, Cn plus 3 for all I care. Is that okay? Just think of what you did when you solved the differential equation. I'm just writing the general thing in a sort of slightly abstract manner. But then what you do, you demand, when you solve this by the power series method or the Frobenius method, what you demand is every coefficient has to vanish, which means this coefficient has to vanish. But since C0 cannot be 0, you insist that S minus S1 into S minus S2 has to be 0. And then what do? You write down the demand that these coefficients must vanish. And since you have already chosen your value of S, usually what will happen is that now you will have to write Cn plus 2 is minus Cn beta ns, depends on n and s alpha, which depends on n and s, and so on. Right? So this gives you a recursion relation. I'm just describing how you solve the problem in a standard approach. Of course, in the standard approach, this will already give you S is either S1 or S2. So instead of S, you will put in S1 or S2, and then you go ahead. Okay? Yeah? That's a standard thing. But suppose, let's just suppose, I did not put in S equal to S1 or S2, but I just did use this recursion relation. Right? I did not use any particular value for S. I just said, okay, let's just write it down. Just write Cn plus 2 is minus Cn beta n comma s by alpha n comma s. So of course, this coefficient will depend on S. So the ratios which you get for successive n will all depend on S. But using that, I can build up the power series. So then I will get C0 into 1 z to the s, of course, plus C2 by C0 is something which has s in it. So some function 1, let's say C1 by C0. Let's just assume it's a one-step recursion relation for the time being. The idea is the same, which depends on s times z, plus f2, which again depends on s times z, the square, plus f3, which again depends on s times z cube, and so on. The dependence on z, s here, is essentially something which makes this be valid, which makes all these coefficients go to 0. So if I did that, then what will the right hand side be? Remember what I'm saying is I did not put in s equal to s1 or s equal to s2. I did not solve the indicial equation. I just left s as a free parameter. But I satisfied all the other recursion relations. Then what will this be? Ly? Yeah. Is what I am describing so difficult to understand?
Sir, I understood what you described, but like I didn't get your question.
What I'm asking is, if I now write down y in this form, where f1, f2, f3, these ratios have all these coefficients, which are essentially C1 by C0 C2 by C0, C3 by C0. They've all been written down in order to satisfy the recursion relations. Okay? And I plug this in, but I have not solved the indicial equation. I'm not putting S equal to S1 or S equal to S2. I just left S as a parameter. If I plug this thing in, okay, equal to 0. If I take this function and apply L on that, what will I get? That should be obvious, by the way. What you will get is exactly just what is left here. All the other coefficients are forced to be 0, right? That's how I chose the ratios. I said that I'm going to satisfy these recursion relations, which means all these are going to be 0. The only term you're going to get at the end of the day is S into S minus 1. Sorry, not S into S minus 1. What you're going to get is S minus S1 into S minus S2 into C0, Z to the S minus 2. Does everybody agree about this? Yes or no? Now you should realize that usually I don't even bother doing something like this because in the end, what I really want is 0, right? So how do I get this thing to be 0? I put S equal to S1, I get this thing to be 0. Or I put S equal to S2, I get this thing to be 0. Is that clear? And usually I don't do it after this much of hard work. I actually start by putting S equal to S1 at the very beginning, which means since S is fixed, this thing does not turn, these ratios don't turn out to be S dependent any longer because I put in the value of S. They of course depend on S, but I put in the value, so they just come out to be some numerical factors. Okay? So that's what we usually do. We just put in S equal to S1 and get one solution. And put in S equal to S2 next, I get another solution. And we are very happy. That is how you really solve it, but you don't do it afterwards. You actually begin by putting S equal to S1 and then finding out the ratios. Right? But you could have done it the other way. You could have actually found out the ratios. They would have all depended on S. And then put in S equal to S1 or S equal to S2 at the end. Now, why am I saying all this? I'm saying all this is fine if you get two distinct roots. But what happens if you get S minus S0 whole square C0 Z to the S minus 2? That is the problem we started out with. If the indicial equation happens to be S minus S0 whole square C0 Z to the S minus 2, then putting S equal to S0 will simply give you one solution, which is fine. It will give you 0, but it will not give you both the solutions. It will give you only one solution. But can anybody
Sir,
tell
we
me?
can
Yeah.
just use the Wronskian and find the other solution.
Of course, you can use the Wronskian and find the other solution. That's one approach. I'm just saying there are other methods which are based on the Frobenius method itself, which is this one I'm talking about. This is just another method which sometimes is more convenient than using the Wronskian. Not always, but sometimes. Okay? So this other method would be you put in S equal to S0. This, after doing all this, you get all the coefficients as function of S. You put in S equal to S0, you get a solution. No problem. Unfortunately, you don't have another S to put in because S equal to S0 is the only root that the indicial equation gives you. But can anybody tell me what will happen if I were to partially differentiate both sides with respect to S and then put S equal to S0? What happens to the right hand side? If I partially differentiate this with respect to S and then put in S equal to S0. You do this and then add S equal to S0. What happens to this? Come on, that's very easy. What is the value of S minus S0 whole square Z to the S minus 2? If you partially differentiate with respect to S0 with respect to s and then put s equal to 0.
So 0 only.
Yeah, it becomes 0. Why does it become 0? Because you get two terms. One will come from the derivative of this, which will have an s minus s0 in it. So it will become 0. The other will come from the derivative of this, but that will have a s minus s0 whole square stuck outside. So that will also be 0. But notice that since L is a linear operator, which involves derivatives with respect to z, I can just push the del s from here right inside. That is, I can differentiate this general solution that I have found out, which does not satisfy the full equation, just satisfies everything but the indicial equation. I can just partially differentiate that with respect to del s and then put s equal to 0. I've got my second solution. Do you understand what I'm saying? If I do this to both sides, the right hand side has vanished. On the left hand side, what happens is you are doing del s acting on the linear operator acting on this. But linear operator involves derivatives with respect to z, and this is a derivative with respect to s. So I can just commute it and move it in. And you're going to partially differentiate this whole thing with respect to s and then put s equal to s0, and you're done. Is that okay? I don't see a lot of agreement. I see only one or two people saying yes. Well, let's see. That is one approach. You write down the solution taking into account the recursion relation without putting in the value of s, and then partially differentiate that with respect to s and put in s equal to s0. But how are we so sure that that is going to give me an independent solution? Isn't it possible that it ends up giving me the same solution with up to a constant? How do we know for sure that that is going to give me an independent solution? And the answer to that is very, very easy. Just think of what happens when you partially differentiate this with respect to s. These are powers of z, right? When you differentiate them, what do you get?
Same powers of z.
You get the same powers of z because the derivatives will be on f1s, f2s, and so on. Right. But there's also z to the s outside, right? So what do you get when you differentiate that with respect to s? Anybody remember that? What is del s of z to the s?
Z to the power s itself.
Z to the power s multiplied by log of
Exactly.
z.
Multiplied by log of z. So this approach will give you the logarithmic solution. End of story. Okay? So that will have a piece which will have a log in it plus another power series. Clear? And since we are at it, suppose you have two roots of the indicial equation which differ by a integer, and as you must have seen before, sometimes these give rise to a situation where one of the solutions is fine, the other one will simply be a multiple of the previous one. And that means you don't get two independent solutions in this situation as well, where S1, S2 are different, but S1 minus S2 is an integer that might very well happen often. But now, will the same trick work? That is, I solve the whole thing without taking into account the indicial equation, plug this in. So I get L z to the S C0 1 plus F1S Z plus F2S Z square and so on. And this is S minus S1 into S minus S2 C0 Z to the S minus 2. Okay. And let's say for S equal to S1, I've got a perfectly nice solution. But can I partially differentiate this with respect to S and put in S equal to S1? And will that give me a second solution? Yes? First tell me this, if I were to differentiate the right hand side partially with respect to S and put in S equal to S1, will the right hand side vanish? It will
No,
not,
sir.
right? Because
Only if S1 is S2.
yeah, because if you had a square, then this will work. But otherwise, when you partially differentiate this factor, it loses the S minus S1 term. So putting in S equal to S1 will not make it vanish. So I need a second power of S1. And the way to do that is write C0. Remember, C0 is an arbitrary constant which is independent of Z. Nobody insists that it's independent of S. So far, we took it to be independent of S simply because making it dependent on S did not serve any purpose. But now what you can do is take C0 to be alpha times S minus S1, which means, of course, you have to do it on both sides. And once you have done that, you have S minus S1 whole square. Partially differentiate with respect to S. Every term will have at least one S minus S1 in it. And when you put in S equal to S1, it is going to vanish. So that's the other trick. Even when two roots differ by an integer, you can still get a solution this way. Is this very useful? The answer is sometimes it is. We already have the Wronskian method to find the second solution, but sometimes the Wronskian is cumbersome to use. Sometimes this is easier to use. Doesn't mean this is the best possible method. This is just easier sometimes, not always. Okay. But it's important to know all the methods available simply because one of the methods may be easier to use in a given situation. Okay, I have exhausted almost all my time talking about standard mathematical methods issues because we have not yet gotten into full-fledged quantum mechanics. But are there any questions about the preliminary lectures that I've uploaded since the last meeting?
Excuse me, sir. I have a question, not from the lectures you have told, but just questioning. The ladder operator, is it exceptionally used for the harmonic oscillator or can be used for any other potential?
Well, the point is finding a ladder operator for an arbitrary potential is almost impossible. Okay, if you could find ladder potential or ladder operators for all potentials, then you could solve all those potentials exactly. Okay. The reason why you can't is simply because the ladder operators have a rather nice and neat geometrical structure. Or, okay, geometrical is Lie algebraic structure to be more precise. And if your potential is very special, you can find ladder operators for them. We will discuss the more general situation later on. But the answer in general is no. But yes, in a way, the harmonic oscillator is not the only problem which allows you to have ladder operators. There are other situations where ladder operators are also available, but they are usually very special situations. So they are in fact, this is a matter of active research in the sense even today, trying to classify all problems where you can have some kind of generalized ladder operator is still going on. The efforts are still going on. Quite a lot of progress has been made. So there's this whole branch called supersymmetric quantum mechanics. Sounds very complicated, and it is in a way. But its upshot is that it allows you to build ladder operator-like structures for a vast range of potentials. Well, the vast range of potentials essentially covers almost all the exactly solvable potentials. Let me also point out that almost, if you take into account, if you try to count how many potentials have exact solutions and try to compare them with the total number of problems possible, the exactly solvable potentials form a set of measure zero, which means they're negligibly small in number, which is why the approximation methods that we are going to talk about, variation, perturbation, and JWKB, they are so very, very important. Put in other words, it's basically like, okay, let me just give you a quick analogy here. Everybody knows what this equation is, right? Where d, of course, stands for ddt. Now, you all know many ways of solving it, but one way which is usually not stressed so much, but is actually great, is this. So basically what you have done is you have factorized the differential equation. Unfortunately, or in this case, it was easy to do because the coefficients were constants. If the coefficients are variable, then factorization will become very, very difficult, and sometimes just factorizing them even like this. For example, even the harmonic oscillator equation, which after a change of variables can look like this, where d here stands for ddx. Well, actually, d squared minus x squared. Is equal to lambda psi. That's what the equation looks like, right? d2 psi dx2 minus x square psi equals lambda psi. Unfortunately, this cannot be factorized as simply as d minus x into d plus x psi equals lambda psi. This doesn't work because d minus x into d plus x is not d square minus x square. Is that okay? The simple rule a plus b into a minus b equal to a square minus b square, of course, doesn't work in general for operators, because what it really gives you is a square plus ba minus ab minus b square. And these two terms don't cancel unless a and b commute. D and x, derivative and x, of course, don't commute. You know that. That's basically, if they did commute, they had commuted, then p and x, momentum and position, would have commuted. So, but you do know the factorization, right? What you do is you write this as p plus I omega x into p minus I omega x, the p square plus omega square x square term, plus p minus I omega x into p plus I omega x. That's how you ultimately land up with the ladder operators. Okay. Now, such factorization is not in general possible for all potentials, but there are potentials for which more complicated factorizations are possible, and for them you have ladder operator like structures. Say for the hydrogen atom, for example, you can find ladder operator like structures, not as simple as these, as the harmonic oscillator ones. In fact, okay, let me just make a sweeping statement. For all exactly solvable potentials, or almost all exactly solvable potentials, you can find a structure like a ladder operator. Is that okay?
Yes, sir. Thank you.
It's also very tough to find those unless you're following some kind of specialized trick like the supersymmetric quantum mechanics that I mentioned. Okay, next. Okay, the last lecture you said three-term recursion relation makes it difficult to handle a potential divergence. Well, There are situations where there are three-term recursion relations and you have to live with them. You can't find a way out. And then you have to take rather complicated steps to sort of handle this. But let me just tell you why a three-term recursion relation is a problem. Say you end up with an equation which is like this: Cn plus 2 plus something into Cn plus 1 plus something into Cn equals 0. This is a recursion relation that you get that tells you that you can find out C2, for example, in terms of C1 and C0, right? So C0, C1 will give you C2. C1, C2 then will give you C3. C2, C3 will then give you C4. In general, all of these will turn out to be, in the end, something which depends on C0 and C1, which is fine. So you will end up with C0 times some solution plus C1 times some solution. Okay. And that's all. This looks perfect because after all, this is a second order linear differential equation which you're trying to solve. So you should get two independent solutions and it looks perfect. It is perfect. If your interest is in solving the differential equation close to z equal to 0 or close to whatever regular point you have, then a three-term recursion relation is not a problem. A five-term recursion relation is not a problem. Okay? Clear? Okay, can anybody tell me why a five-term recursion relation is not a problem even if you had a second order differential equation? Five-term recursion relation would be Cn plus 4, Cn plus 3, Cn plus 2, and Cn. 5 is just a number I cooked up. All I'm saying is anything more than 2 should not be a problem. Can anybody tell me why it should not be a problem? Because if it's a five-term recursion relation, then C5 should come out in terms of C0, C1, C4 should come out in terms of C0, C1, C2, C3, right? Then C5. Okay, let me just cook up one such equation. Let's say y double prime. I'm just making this up, but should not be very difficult to find one. Y double prime gives you z to the n minus 2, right? Y, you want z to the n minus 1. Okay, z to the n minus 2. I want 5 different powers. How do I get 5 different powers? I can just put in z plus z square. Say 1 plus z square plus z cube. So this will give me n minus 2. This will give me n plus 1, n minus 1, n plus 2, n plus 3. So from Cn z to the n, you will get 5 different powers, and when you try to push them all to Cn z to the n, you will end up with a 5-term recursion relation. The question I am asking you here is this. So if you have a 5-term recursion relation like this one, you will get C4 in terms of C0, C1, C2, C3, C5 in terms of C1, C2, C3, C4, and so on. So it looks like you get C4, C5, C6, C7, all subsequent terms in terms of all subsequent coefficients in terms of C1, C2, C3, and C0. All of them. Can you tell me why this should be a problem? Okay, Aniruddha Datta has said that, has pinpointed the problem. The problem is we can have at most 2 arbitrary constants. And Shayan, I think, has already given us a solution to that. The solution is, if you wrote down all the equation in full, you will find that you will get this 5-term recursion relation, but you will also get a lot of equations from the lower powers, which will force some of these coefficients, in particular C2, C3, to be expressed already in terms of C0 and C1. Which means although the recursion relation seems to tell you that C4 depends on C0, C1, C2, C3, and so on, ultimately everything will end up depending on C0 and C1. Don't take my word for it. you should at least take this equation and try to write down a power series solution for this, at least the first few terms. And this here z equal to 0 is a regular point. Should not be a problem finding out a solution. Okay. So this, of course, is going entirely in the other direction to the question that Gurpahul asked. Gurpahul asked, I had said that having a 3-term recursion relation is problematic. Okay. And now I'm telling you that having a 3-term, 4-term, 5-term recursion relation is not a problem. So how do we reconcile these two entirely opposing statements? The answer to that is this. If all I ever wanted to do is find out a power series solution which is well behaved close to z equal to 0, and if I knew, say, for example, the initial conditions at z equal to 0 to find out the constants in front, then this is perfect, no problem. I have no issues whatsoever with this solution. However, what we do want is to ensure that the solution stays well behaved close to a singularity. So to handle the behavior close to a singularity rather well. That is a problem. Why is that a problem? Because one of the simplest ways of handling things when things go out of hand, like when the solution blows up, you should listen to those lectures very carefully, because there I explain how you know this. How you know beforehand that the solution is going to blow up? Because you have singular points. And near the singular points, the solution has to blow up. You know that. But how do you check that your solution blows up? You essentially take a look at what happens to high powers and take the limits and take the ratios and so on. But once you know it blows up, how to prevent that from happening? Simple thing is, if you had a 2-term recursion relation like Cn plus 2 is something times Cn, all you do is say, you put in C6, not 0, but C8 0. That, of course, will tell you something about this coefficient. And this is where the quantization actually comes from, by the way. This tells you that some parameter has to take only certain specific value. But notice that once C8 is 0, this immediately tells you C10 is 0, tells you C12 is 0, C14 is 0. All subsequent even powers vanish in one go. Okay. Because you have a 2-term recursion relation, the next term comes from the preceding term. So if once a term vanishes, all further terms vanish. But if you have a 3-term recursion relation, something like Cn plus 2 is something into Cn plus 1 plus something into Cn, then I can't get a polynomial solution out of this at all. I can't make it truncate. Why? Because I can possibly choose our parameters in such a way that these two coefficients will conspire to make Cn plus 2 vanish. Okay? Say, make C8 vanish, even though C6, C7, etc. are not 0. But then C9 will not depend on C8 alone. It will depend on C7 as well. So unless you are very, very lucky, C9 will not be 0. C9 could vanish if there were some very special combination of coefficients which made it vanish also. And if, of course, both C8 and C9 vanish, then C10, C11, all of them will vanish. But in general, what will happen is you can make C8 vanish, but that will not allow C9 to vanish, because C9 then will be something else into C8 plus something into C7. And of this, only C8 is 0. C7 is not, neither is the coefficient in front. And that means even if you make a solution vanish at a particular power vanish, or coefficient of a particular power vanish, the subsequent powers will not vanish, and you will still end up with an infinite series. And an infinite series is what you want to avoid at this stage. Is the answer clear? So 3-term recursion relations, if you can't avoid them, you have to handle them by special techniques. But if you can avoid them, and it so happens that as long as you know that you have a well-defined solution at infinity or at z equal to plus minus 1, depending on where your singularities are, you know you can get a well-defined, well-behaved solution, then there should be a way of getting a 2-term recursion relation. Once again, the lesson is look for the singularities, look at the behavior close to the singularities, so that you are forewarned about what kind of problems you can face. and try to nip them in the bud. Or at least, if you can't, try to control them as much as possible. Okay. So the future, well, today, I think by tonight, you will get part 4B. The only reason I broke it up into 4A and 4B is that they were getting too long. So instead of pushing 90 minutes or 1 hour, 40 minutes of a video, I just broke it up into 2. But 4A and 4B deal with the angular part of a solution for 3D, which also is the theory of angular momentum in coordinates, as opposed to the raising or lowering operators. So that's covered in part 4A and 4B. 4A has already been up. Not everybody has taken a look at them. I can make out that, but at least not the full lecture. But fine, 4A is something which you already perhaps know most of. But still there are things there which may not be very obvious to everybody. And 4B discusses the associated Legendre equation, how to solve it, what kind of solutions you get, and the spherical harmonics which come in as a result of this, and some properties. So that's the angular part. The next part will be on the radial equation, which will involve, among other things, the hydrogen atom. But we will keep 2 or 3 other examples as well, just to show that this can be used not only for the hydrogen atom, but for other things. And that will cover our preliminary lectures. Okay. I will try to throw in a Sturm-Liouville equation lecture somewhere in between, but that will be primarily a way of seeing all these differential equations together under one umbrella, so to speak. But that's not essential. That's just mathematical physics. That's not really so much quantum mechanics. It's just that you use that in quantum mechanics very often. And once the hydrogen atom is out of the way, I hope by next week to start on the radiational method. And before you come to the lecture next Wednesday, I would expect you to have watched at least all the lectures, at least the ones which are on the new topics. And on next Friday, not day after tomorrow, but next Friday, in the slot that is supposedly free for all of you, we will have a class test, our first class test. We will cover all of the preliminary topics. Okay? Any questions? Okay, Gurpahul asked a question, which is, also, how do we know from which nth coefficient we need to truncate? We don't. In fact, you truncate at any one of the nth coefficients, you will get a polynomial solution which will be well behaved at the singularity. So which is why you get multiple solutions. If we had chosen truncation at some other n, we might get an entirely different function. You don't get entirely different functions, you get an entirely different function. The different Hermite polynomials are all different functions, right? They're not the same function. They're different functions with different nodes.
Sir, right. But like if we choose if we truncate for Cn plus like for C2, if we truncate at C2 for the ground wave function,
you can't truncate a C2 for the ground wave function. That's where you're going wrong. Okay. The point is you get a bunch of solutions. All these solutions, unless you choose special value of lambda, would diverge at plus infinity or minus infinity or both. And if you want them to converge at plus minus infinity both, I'm again talking in terms of the Hermite equation or in terms of the harmonic oscillator, but the general statement is true for all systems, except that for all systems you can't get these nice two-term recursion relations which allows you to explicitly find the lambda. But anyway, if you can, then Lambda equal to 1, 3, 5, 7 are ones for which you have well-behaved solutions, and those are your eigenfunctions. So you get all the eigenfunctions, not just one of them or two of them. For the ground state, you cannot choose to make C2 0. The point is, if you make, or rather, that's wrong. Actually, you can choose to make C2 0, and that's how you get the ground state. If you choose to make C4 0 and not C2, then you get the second excited state. You choose to make C3 0, you get the first excited state. Is that okay?
Okay, sir. Got it.
And all of these functions are classified as a single set of polynomials. Not one polynomial, but a bunch of polynomials which go together, which have these nice recursion relations. They come from a Rodrigues formula and so on. Okay, if there are no other questions, we will fold up today. Is there a way to derive the generating function from the DE? Yes, but that requires some more nifty, what do you call it, complex analysis. Integral transforms. I'm just throwing in that in as a word because that's a bit too advanced right now to go into right now. Okay, so let's call it a day today. Next Wednesday, we meet again, and next Friday, the Friday after that, we have our first class test. Okay, bye.